NASA's Deep Space Network detects something impossible. Pioneer 10, launched 8 years earlier to explore Jupiter, is not where it should be. The spacecraft is falling behind its projected position by thousands of kilometers per year. Not a lot, just enough to be measurable, and completely unexplainable. The force slowing Pioneer is tiny, 8.74 plus or minus 1.33 times 10 to the power of minus 10 meters per second squared. To put that in perspective, it's about 10 billion times weaker than Earth's gravity. You could barely measure it in a laboratory, but over millions of kilometers and decades of travel, this microscopic deceleration adds up. By the 1990s, Pioneer 10 was lagging 400,000 kilometers behind where Newton's laws said it should be. That's the distance from Earth to the Moon. And here's what made physicists lose sleep. Pioneer 11 showed the exact same effect. Two spacecraft, launched a year apart, traveling in different directions through the solar system, both experiencing identical unexplained deceleration toward the Sun. This wasn't random. This wasn't measurement error. This was something systematic, something consistent, something that suggested our understanding of gravity itself might be wrong. The question wasn't just, what's slowing them down? The question was, do we need to rewrite the laws of physics? Let me show you what should happen when spacecraft travel through the solar system. Newton's law of universal gravitation, published in 1687, states that every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. This law has been tested countless times. It predicts planetary orbits. It guided the Apollo missions to the Moon. It's one of the most thoroughly validated principles in all of science. When Pioneer 10 launched on March 2, 1972, NASA engineers calculated its trajectory using Newton's laws. They accounted for the gravitational pull of the Sun, Jupiter, Saturn, and every other significant mass in the solar system. They factored in solar radiation pressure, photons from the Sun pushing gently against the spacecraft. They included the solar wind, charged particles streaming outward from the Sun. They even considered the tiny drag from interplanetary dust and gas, though the vacuum of space is so complete that this effect is negligible. The math worked perfectly. Pioneer 10 flew past Jupiter on December 3, 1973, using the planet's gravity to slingshot onto a trajectory that would carry it out of the solar system forever. Pioneer 11 followed in 1974, visiting Jupiter and then Saturn before heading outward. Both spacecraft were equipped with radioisotope thermoelectric generators, nuclear batteries using heat from decaying plutonium-238 to generate electricity. These RTGs would provide power for decades, allowing the spacecraft to transmit data as they journeyed into interstellar space. And for the first few years, everything matched predictions. The spacecraft were exactly where they should be, traveling at exactly the speeds they should be. But in the 1980s, as the Pioneers moved beyond Saturn's orbit and deeper into the outer solar system, navigation engineers at NASA's Jet Propulsion Laboratory started noticing discrepancies. The Doppler shift in the spacecraft's radio signals, which reveals velocity with incredible precision, showed the spacecraft were slowing down slightly more than expected. At first, they assumed it was measurement error, tiny uncertainties in tracking. Maybe the spacecraft clocks were drifting. Maybe there were unmodeled thermal effects in the radio transmitters affecting the signal frequency. But as years passed and data accumulated, the pattern became undeniable. Both Pioneers were experiencing a constant sunward acceleration of about 8.74 times 10 to the power of minus 10 meters per second squared. This is where things get strange. Because this tiny force couldn't be explained, by anything in the standard model of physics. Solar gravity? Already accounted for, and it decreases with distance squared. Solar radiation pressure? Also accounted for, and it too falls off with distance. The gas leaks from thrusters. The pioneers weren't firing thrusters, they were coasting. Heat radiated from the RTGs? Engineers assumed this would be roughly symmetric, canceling out. Drag from interstellar medium? Far too weak at these distances. Every conventional explanation failed. By 1998, when physicist Michael Martin Nieto and astronomer John Anderson published the first comprehensive paper analyzing the anomaly, the physics community took notice. Here was a measured effect that violated known physics. Either something was very wrong with our measurements, or something was very wrong with our theories. Before I reveal what scientists eventually discovered, and why it took 20 years and a heroic data recovery effort, if you want to follow mysteries like this as they unfold, hit that subscribe button. But we're covering real scientific detective work, where researchers chase down decades-old data stored on obsolete magnetic tapes to solve cosmic puzzles that threaten to overturn everything we know about gravity. The investigation into the Pioneer anomaly became a who's who of theoretical physicists proposing exotic solutions. Could there be dark matter concentrated near the Sun, creating additional gravitational drag? Could Einstein's general relativity need modification at very large distances? Could the cosmological constant, the mysterious dark energy causing the universe's expansion to accelerate, somehow affect spacecraft motion within the solar system? Some proposed that the speed of light might not be constant, varying slightly with distance from massive objects. Others suggested new fundamental forces, a fifth force beyond gravity, electromagnetism, strong nuclear, and weak nuclear. Still others wondered if the pioneers were encountering some kind of quantum foam effect, where space-time itself becomes turbulent at microscopic scales. But there was one mundane possibility that kept coming up: thermal radiation. The RTGs on each Pioneer spacecraft generated about 2,500 watts of heat at launch, declining slowly as the plutonium-238 decayed. This heat had to go somewhere. In the vacuum of space, it could only escape through infrared radiation. And if that radiation wasn't perfectly symmetric, if more heat radiated in one direction than another, it would create a recoil force, like a very weak rocket engine. The problem was proving it. To model the thermal radiation precisely, researchers needed detailed information about the spacecraft's design. How much heat did each component generate? What were the reflective properties of every surface? How did the spacecraft's spin affect heat distribution? Most crucially, which direction was most of the heat radiating? And here's where the story becomes a data recovery thriller. The Pioneer missions launched in the early 1970s. By 2006, when physicist Slava Turishev at JPL began seriously investigating the thermal hypothesis, much of the original mission data had been lost or was stored on obsolete 7-track and 9-track magnetic tapes that could no longer be read by modern computers. Mission documentation existed only on paper blueprints in storage facilities. Many of the original engineers had retired or passed away. Turishev needed funding to recover this data. NASA's budget had moved on to new missions, but the Planetary Society, a non-profit space advocacy organization, stepped in. With funding from their members, Turishev and his team launched an archaeological expedition through NASA's archives. They hunted down tape drives capable of reading 1970s-era formats. They digitized thousands of pages of engineering drawings. They tracked down Doppler tracking data that had been considered too voluminous to permanently archive and had been scheduled for destruction. They found telemetry records stored in basement storage rooms. They interviewed retired engineers who remembered obscure design details. The data recovery took years, but by 2010, Turyshev and his colleague Viktor Toth had assembled the most comprehensive dataset ever compiled on the Pioneer spacecraft. They began building a thermal model. They started with the RTGs. Each Pioneer carried 4 of these nuclear batteries mounted on booms extending from the spacecraft body. The RTGs generated heat, which radiated in all directions, but not equally. The spacecraft's design created asymmetries. The large high-gain antenna, a 2.7-meter dish used to communicate with Earth, sat on one side of the spacecraft. Heat from the RTGs reflected off this dish, bouncing backward. Additionally, the warm electronics box was positioned such that it radiated more heat forward than aft. The team built a finite-element thermal model incorporating every component, every surface, every heat source. They ran simulations using actual flight telemetry as boundary conditions, and they calculated the recoil force from thermal photons streaming preferentially in certain directions. The result? A predicted deceleration of 8.55 plus or minus 0.86 times 10 to the power of minus 10 meters per second squared, within error bars of the observed anomaly. The magnitude matched, the direction matched, the time variation matched. As the RTGs decayed and produced less heat, the anomaly decreased, exactly as observed. In July 2012, Turyshev's team published their findings in physical review letters. The conclusion: once the thermal recoil force is properly accounted for, no anomalous acceleration remains. The Pioneer anomaly was solved. It wasn't new physics. It wasn't dark matter or modified gravity or exotic quantum effects. It was heat. Infrared photons carrying away energy, creating a tiny but measurable rocket effect. The spacecraft were literally being slowed by their own waste heat, radiated preferentially in the forward direction. But here's the twist that some researchers still debate. The thermal model explains about 80 to 90% of the anomaly. There's a remaining 10 to 20% that's statistically consistent with zero, meaning it could just be measurement uncertainty. But some researchers argue there might be a tiny residual effect still unexplained. And Pioneer 11's data wasn't analyzed in as much detail as Pioneer 10's, leaving some uncertainty about whether both spacecraft showed identical behavior. Moreover, both Pioneers experienced anomalous spin-down. Their rotation rates decreased faster than expected. The thermal model suggests this could also be due to asymmetric heat reflection off instrument sunshades. But this hasn't been proven as definitively as the deceleration anomaly. So here's what I genuinely want to know from you. After seeing how 20 years of investigation revealed a mundane thermal explanation for what looked like physics-breaking deceleration, do you think there's still something mysterious about the Pioneers? Option A. Fully explained. The thermal radiation model accounts for everything within measurement uncertainty. No new physics needed. Option B. Mostly explained, but questions remain. The 10 to 20% residual and the spin-down deserve further investigation. Option C. Still mysterious. The thermal explanation is too convenient. Something else is happening that we haven't discovered yet. Drop your vote in the comments. Because this story raises a deeper question about science. How do we know when we've truly solved a mystery versus when we've just found an explanation that fits the data well enough? Here's why this matters beyond 2 spacecraft from the 1970s. The Pioneer investigation taught us that even in an era of computer modeling and modern physics, we can still be surprised by simple thermal effects. It showed that solving cosmic mysteries sometimes requires detective work through archives and data recovery as much as theoretical brilliance. And it demonstrated that citizen support, through organizations like the Planetary Society, can fund crucial research that might otherwise never happen. The thermal radiation effect discovered on the Pioneers is now called the Pioneer effect, and must be considered for all deep space missions. New Horizons, launched to Pluto in 2006, was designed with its RTG mounted close to the spacecraft body precisely to minimize thermal recoil forces. Future missions account for these effects in trajectory planning. And the investigation spawned new research into thermal modeling of spacecraft. Engineers now use sophisticated computer simulations to predict how heat distribution affects trajectories. This has applications for everything from Earth-orbiting satellites to interstellar probes. But for some researchers, the Pioneer story remains unsettling. Because what if there is a tiny residual effect, something 1 or 2 orders of magnitude smaller than the thermal anomaly, that we still can't explain? What if buried in that remaining 10 to 20% uncertainty is a genuine hint of new physics? We'll likely never know. A Pioneer 10's last signal was received on January 23, 2003. Pioneer 11 went silent on September 30, 1995. Both spacecraft continue coasting through interstellar space, now beyond our ability to track. They'll drift for millions of years, eventually becoming interstellar flotsam in the void between stars. But they've left us with a lesson. Sometimes the most interesting scientific discoveries aren't new laws of physics. Sometimes they're the subtle, overlooked effects hiding in plain sight. Effects we thought were too small to matter, until precision measurements revealed they were everything. And sometimes, solving a mystery doesn't give you the answer you want. You hope for new physics, for exotic phenomena, for revolutionary discoveries that rewrite textbooks. Instead, you find out it was just heat, bouncing off an antenna dish, creating a tiny rocket effect that no one bothered to calculate carefully until spacecraft started acting strange. The universe is full of mysteries, but the Pioneer anomaly reminds us that not every mystery points to unknown physics. Sometimes it just points to unknown spacecraft thermal dynamics. And sometimes that's the more important lesson. If you want to follow current space mysteries, from fast radio bursts to dark matter detection experiments to the search for Planet 9, subscribe. We're tracking the investigations happening right now, chasing down the anomalies that might be the next big discovery, or might just be another heat effect we forgot to model. The Pioneers are gone now, silent and unreachable. But their legacy lives on in every precision spacecraft tracking measurement, every thermal model, and every reminded that even the simplest explanations sometimes require decades of work to prove. And somewhere out there, about 15 billion kilometers from Earth, Pioneer 10 is still traveling at 12 kilometers per second, still slowing ever so slightly from the dying warmth of its plutonium core. Still teaching us, even in silence, that the universe's greatest mysteries sometimes have the most mundane answers. See you in the next one.